Hello everyone, welcome to this presentation called Algorithms for the Solution of the Navier-Stokes Equations for Transient Incompressible Flows. My name is Hugo Castillo Sanchez, and in the previous videos that can be found in my channel, we focused on solving the Navier-Stokes equations for very basic flow problems, such as simple shear flow and shear flow with pressure gradient. And in those problems, we neglected the temporal and convective terms of the Navier-Stokes equations to derive a steady-state solution for the velocity profile. However, there are flow cases where we are interested in studying the transient behavior, and also there are realistic flow scenarios where we have to consider all the terms of the Navier-Stokes equations, and thus we have to develop and use algorithms that could allow us to solve those equations. And for these reasons, I would like to give a brief introduction to some of the algorithms that are used in CFD to solve the Navier-Stokes equations. So this is going to be a two-part lecture series where we will be talking about these algorithms. In part one, I want to illustrate the projection methods. So a quick overview of this presentation. In order to explain what is a projection method, I need to explain first what is the Helmholtz-Hodge decomposition for vector fields, and then once that we understand this decomposition, I will give an introduction to projection methods, where we will be talking about the incremental and non-incremental version, and also I would like to discuss a bit about the temporal discretization methods of the Navier-Stokes equations that includes the explicit Euler and semi-implicit Euler. So the Navier-Stokes equations for incompressible flows. So these equations express mathematically the momentum and mass conservation for Newtonian fluids. We already discussed in one of my previous videos what is a Newtonian fluid. So I assume that you understand this concept, and if you are not familiar with this term, I will recommend you to watch one of my previous videos. But basically, Newtonian fluids are those fluids where there is a linear behavior between the shear stress and the shear rate. So Newtonian fluids describe very simple fluids, such as water. And for incompressible fluids, that means fluids like liquids. For incompressible fluids with constant physical properties, the Navier-Stokes equations are composed of a system of equations. The first one is the continuity equation, which is just the mass conservation, which is this divergence of the velocity field. That divergence has to be equal to 0. So this, physically speaking, this equation tells us that the mass is conserved in any point of space of our system. And then we have the momentum conservation equation, which is just Newton's second law for fluids. You remember Newton's second law, that law expresses that the acceleration of a body is equal to the external forces acting on that body. And for fluids, it's similar. So we have on the left hand side of the equation, we have two derivatives, two accelerations. The first one is the temporal derivative, which is just the derivative of the velocity with respect to time. And then we have a spatial derivative, which is the convective term. So we have the gradient of the velocity multiplied by the velocity. This derivative tells us how the velocity varies in each direction, x, y, and z, in the direction of the velocity. And those two accelerations have to be equal to the forces acting on the fluid. So here in the first term, we have the pressure gradient, which is just that term where, for instance, there is the presence of a mechanical device such as a pump. A pump can change the pressure of fluid. In this term, we have the Laplacian term, which is just the second derivative of the velocities. And then we have the source term, because there might be external forces also acting on our fluid, for instance, an electromagnetic field or the gravitational forces. And here I'm including in this diffusive term, I'm including the Reynolds number, which is a very important non-dimensionless number in fluid dynamics, which just compares the inertial forces with viscous forces. Yeah, F is the source term. I'm using here the bold notation, which represents these bold letters represent vector quantities. So the velocity is a vector that is going to depend on both position and time. And P is the pressure. P is also going to depend on position and time. And these two quantities, velocity and pressure, are defined in a d-dimensional domain. So the domain is omega, and omega is part of the real numbers. So D can be either 2 or 3 dimensions. So that means that these two equations can be solved in a 2-dimensional domain or in a 3-dimensional domain. So as I was saying before, these bold letters express vector quantities. So these two equations are actually a system of 4 equations, of 4 partial differential equations. So if we assume Cartesian coordinates, so that means that the velocity will have 3 components, one velocity in x direction, another one in y direction, and another one in z direction. So these equations, the ones that are here, can be expressed as follows. So this is a very complex system of partial differential equations where we have temporal derivatives, we have convective terms or spatial derivatives, we have the pressure gradient, the Laplacian, which is how the velocity varies in each direction, the second derivative of the velocity in each direction, and then plus the source term. So we have one equation for velocity ux, another one for uy, and another one for uc. And then we have the continuity equation, which is just the equation that I show here. So some important points to consider. So the Navier-Stokes equations are a coupled system of 4 partial differential equations with 4 unknowns. So you can count these equations, and then we have 4 variables. We have the velocity, the 3 components of the velocity, and also the pressure. And you can notice that the equations are expressed in terms of the velocity profile, the vector velocity field, but there is no equation for pressure. So this is something important to consider. For compressible fluids, that means gases, we could use an equation of a state. If you took some thermodynamic lectures, you might be familiar with the ideal gas or Van der Waals or Penn-Robinson equation of states. So we could use these equations to compute the pressure. But as the title of the presentation says, we are interested in studying incompressible fluids, such as liquids. So for these cases, there is no equation for pressure. So that means that we have a strong coupling between velocity and pressure. So that means we cannot compute the values of the velocity without knowing the value of the pressure, and vice versa. We cannot compute the pressure value without knowing the values of the velocity field. So that's a problem that we have to solve. And in CFD, the continuity equation is used as a physical restriction of the system that must be satisfied. So that means that besides solving these equations, we also have to satisfy this equation, that is just mass conservation. So for every flow problem that involves incompressible fluids, we have to solve these equations. That means we need to find both P and velocity, but also the velocity field that we find has to satisfy this equation. So many methods have been developed since late 60s. So this has resulted in different approaches to deal with the strong coupling between velocity and pressure in the incompressible Navier-Stokes equations. So as you will see at the end of this talk, in the majority of these methods, the momentum and mass conservation equations are used to derive an equation for the pressure, for P. And one of these methods, which is the goal of this talk, is to explain or to give an introduction to the projection method or fractional step method, which employs the Helmholtz-Hodge decomposition. So you will see, you will understand this idea in a few slides, but the idea of this decomposition is that it will split the velocity field of the Navier-Stokes equations in two parts, one that is irrotational and another one that is solenoidal. So once that we splitted this velocity field, it will allow us to compute the velocity and pressure. So Helmholtz-Hodge decomposition. So this decomposition is one of the fundamental theorems in fluid dynamics. It has been used several times and by researchers. You can find plenty of information about this decomposition in the literature. So as I was saying before, this decomposition decomposes a vector field into components, one that is divergence-free and another one that is solenoidal or rotation-free component. And yeah, this decomposition is important because it simplifies the analysis of vector fields, since some important properties like vorticity and incompressibility can be studied on the components directly. So I describe this with sentences, but now let's talk about mathematics. So let's define a vector field F. So remember, the bold notation means that we have a vector field. So this vector F, is going to be located in a bounded domain omega. And this domain has a smooth boundary. So that means this boundary will not have edges or corners. So this smooth boundary can be represented as delta omega. And the Helmholtz-Hodge theorem states that the vector field F, and it has to satisfy this surface integral. This is a mathematical property that has to be satisfied in order to use this decomposition. So this vector field F can be decomposed as a sum of a divergence-free vector, which we will call U. So divergence-free means that the divergence of this vector U has to be equal to 0. And then the second component of this decomposition will be a curve-free vector field that we will call UV. And remember, the curve-free means that the rotational has to be equal to 0. So F can be decomposed as a sum of two vector fields, U and B. Remember, U is divergence-free and B is curve-free. So since UV is curve-free, there also, you remember your calculus lectures. So if this vector is curve-free, there exists a scalar function that we will call P in such a way that this B can be expressed as the gradient of this scalar function. So now this equation F can be expressed as the sum, the vector F can be expressed as the sum of the divergence-free vector plus the gradient of this scalar function. So P is a scalar potential function, this is its gradient, and this is the divergence of U. So you can find more information about this decomposition in this paper that it will be found in the references at the end of this presentation. So some important points that I also want to mention is that also remember from your calculus lectures that you can decompose a vector field into normal components and tangential components. So the normal components of both the vector F and the vector U have to coincide at the boundary of omega. Also the vector U, you can find this in the literature, that the vector U can be also called as solenoidal field or rotation field, and the vector UV is also called gradient field. And you will see that this decomposition is often used to design numerical methods to solve the Navier-Stokes equations, by means of segregating the coupled system of equations, creating a sequential and more efficient way to compute U and P. So this will be clearer in a few slides. But before explaining those algorithms, I want to explain that the idea of these methods is to decompose a known vector field. So that means in order to use this decomposition, we need to know beforehand the vector field F in order to calculate U and P. U, remember, is a divergence-free vector, and P is the scalar that was defined here. So to achieve this, we need to solve a Poisson equation, which can be obtained by applying the divergence operator in both sides of this equation that was defined, equation 4. So we will apply the divergence operator in both sides of this equation. So we will end up having this equation. But remember that from our definitions, the vector field is the vector field U is divergence free here. So this term is actually 0. So this equation 5, becomes equation 6. So we have an equation that can be solved easily because we know F. We just need to obtain its gradient, and that has to be equal to the Laplacian, or the divergence of the gradient of P. So this operator becomes a Laplacian. So this full equation is a Poisson equation that can be solved using this boundary condition, which is a Newman boundary condition. That means that at the boundary we need to satisfy this condition. So once that we have solved the Poisson equation to find P, we compute the vector U as follows. So we just from this equation we just isolate for U, and then we end up with this equation, with equation 7. So these ideas we will be used to explain the projection methods. So we will describe two types of projection methods that will allow the decoupling of U and P. So remember, one of the main problems or one of the main challenges of solving the Navier-Stokes equations is that there is a strong coupling between velocity and pressure. So this method will allow us to decoupling velocity and pressure, and this will be used to solve the Navier-Stokes equations for transient flows of incompressible fluids. So I will explain first the non-incremental method, and then we will move into explaining the incremental method, which is also called pressure correction method. So to illustrate these methods, I also want to explain, or to give an introduction to temporal discretization of the Navier-Stokes equations. So we will use the explicit Euler method, which allows us to compute an approximation for the new state given the current state. So the goal of the explicit Euler method is that we want to find the new solution of the velocity based on a previous value of the velocity. So for instance, let me define some variables or some constants. So we will be interested in solving the transient behavior of a fluid using the Navier-Stokes equations. So I'm going to use this term, which is delta t, which represents the time step. The index n will stand for the current time, or the old state. The velocity with index n is the velocity value in the current time t, and n plus 1 is the new solution, t plus delta t. So in explicit Euler method, we need to find, our goal will be to find the new value of the velocity at the new time, which will be t plus delta t. So this n plus 1 means the value of the velocity at this time. So in order to estimate u n plus 1, we will be using the information that we obtain at the current time or at the old state. So that means the velocity values at the previous time step, and also plus the other terms from the Navier-Stokes equations. So if we discretize the Navier-Stokes equations, which can be found here, equation 2, if we carried out a temporal discretization of the Navier-Stokes equations, so that means the explicit Euler method, so the temporal derivative can be expressed as just this difference, which will see, we obtain this equation from the left-hand side of the equation. We have the velocity at the new time, the one we are interested in calculating, minus the velocity at the current time or at the old state, divided by delta t, the time step. So that has to be equal to the convected term that will be calculated at the previous time or at the current time. Plus we have the Laplacian that will also be evaluated at the old state, plus the source term that is also evaluated at the old time. But here, an exception, we will be evaluating the pressure at the new time, because remember, pressure is also a variable. We don't know the value of pressure, so we need to compute the value of the pressure at the new time. So we will use this value of the pressure also to estimate the new value of velocity. And also remember, we have to satisfy the continuity equation. So that means that the divergence of the new velocity, this one, has to be equal to 0. So how do we solve this system of equations? So we will be using the non-incremental projection method. So in this method, we initially ignore the pressure gradient. So that means we will neglect this term by now. And we will calculate an intermediate velocity, which we will call U star, which will be between the steps n plus 1 and n. So that's why this projection method is also called fractional step method, because we will be estimating velocity that will be found between these two velocities evaluated at n plus 1 and n. So if we use this intermediate velocity, we will derive an equation, a Navier-Stokes equations for this U star. So we end up with this equation. So remember, we are ignoring this pressure gradient term. So we have this equation, equation 10, that will depend on U star. Yeah, the other terms remain the same. So something important is that U star needs to satisfy the same boundary conditions as U, the original velocity, but U star is a vector field that will not satisfy the continuity equation. Or in other words, this velocity field U star is not solenoidal. That means that the divergence of the U star is not going to be different. It's going to be different than 0. So remember this idea is going to be important later. So now we will apply the Helmholtz-Hodge decomposition, and we will correct the intermediate velocity, adding the pressure gradient to obtain the final velocity. So we have equation 11. So this equation 11 can be obtained by obtaining the difference between equation 8 and equation 10. If you apply the difference between these equations, you will end up with this equation, where we have the velocity we are interested in calculating, which is the velocity at the new time, minus the velocity, the intermediate velocity, divided by the time step. That has to be equal to the pressure gradient at the new time. So from this equation, we can isolate for U n plus 1, and we end up with this equation on the right. So now we will do some algebra. We will apply the divergence in both sides of this equation. And remember that in equation 9, we specify that U the velocity at the new time has to satisfy the continuity equation. So it's called the incompressibility condition. So you can see where we are heading to. So if we apply the divergence in both sides of this equation, we will end up with this equation, equation 12. So this is a Poisson equation for pressure. Remember, by solving equation 10, we know the value of the U star, or of the intermediate velocity. So this equation can be solved easily by applying this boundary condition at the boundary, Newman boundary condition. So once that we solve equation 12, we can calculate the pressure at the new time. And once that we have this piece of information, we can obtain the new velocity, the velocity u n plus 1 as follows. So we use this equation to estimate u n plus 1. So remember, we obtain u star by solving this equation. We obtain the pressure by solving the Poisson equation. And now we have our new velocity that will satisfy the incompressibility condition, or the continuity equation. So now we have an algorithm for the non-incremental method. So how do we solve the Navier-Stokes equations? So here I include a summary of the algorithm. So we solve the Navier-Stokes equations. The first step is initialize the pressure and the velocity field at time t equal to 0. So that means that we will apply initial conditions. So that means we will assign values to Pn and Un. And then we will also fix boundary conditions. So these boundary conditions depend on the specific problem you are working with. For instance, in a channel flow, you can use non-slip boundary conditions. And then once that you do step 1, you enter the temporal loop. So that means you will be increasing delta t values to increase time. And then the first step of the temporal loop is that you will solve the momentum equation to compute the non-divergence free velocity. So that means that the first step of the temporal loop is that you need to solve this equation, equation 10, to obtain the U star. Once that you have U star, now you move to step 2, which is solve the Poisson equation, equation 12, to estimate P, the pressure at n plus 1. And once that you have these two pieces of information, you correct the velocity as follows with the equation 13. And now you update all the fields to be used in the next time loop. So the velocity and the pressure values that you obtain in this loop will now be used in the next time step. So that means that the solutions we obtain for velocity and pressure will now be the all-time state of the new temporal loop. So you go, once that you obtain this, you find u and p at n plus 1. Now you increment the time, so that means you add delta t, and then you return to step 2. So you enter again the temporal loop, and then you solve these equations again, and then you obtain the new values of velocity and pressure, and so on. And then you enter this temporal loop until the final time is reached. So the non-incremental version tends to be of order delta t. So that means that you have to use very small values of delta t in order for your method to be stable. Because otherwise, if you use slightly larger values of delta t, you might observe some errors. Your velocity values and pressure values can have some errors. So you have to be careful with using your values of delta t. So incremental projection method. So now the main difference with this incremental projection method compared to the non-incremental projection method is that we will be consider the value of the pressure at the current time or at the old state to estimate the intermediate velocity u star. So remember, in the non-incremental projection method, which is equation 10, we didn't consider the pressure. But here, for the incremental version, we will consider it. And then we also have to satisfy the incompressibility condition for the new velocity value. That means un plus 1. And then by applying the Helmholtz-Hodge decomposition, we will correct the intermediate velocity that will be obtained by solve equation 14. So yeah, we do this correction by adding the pressure gradient to obtain the velocity, the final velocity un plus 1. So we obtain equation 16 that can also be obtained by obtaining the difference between equation 8. You have equation 8, and then you obtain the difference with for equation 14, and then you end up with this equation 16. So you have the difference between the new velocity minus u star that was calculated using equation 14 divided by delta t. That has to be equal to a difference between pressures. The pressure that is a variable, we need to also find Pn plus 1 minus the pressure at the current time, pressure at Pn. So let's define this variable, which we will call phi, which is just the product between delta t and the pressure difference. And then we will derive a Poisson equation, but now in terms of this variable that we just defined, phi. And then we will derive this equation by applying the divergence in both sides of the equation, of this equation. So remember, we will apply the divergence operator in both sides of this equation. Remember, we also have the incompressibility condition for the new velocity, which is this one. And then you end up with equation 17, which is also a Poisson equation, but now in terms of phi. So we also have to satisfy this boundary condition, Newman boundary condition for phi. And yeah, equation 17 can be solved. And then you obtain phi. And now the new velocity can be calculated as follows. We isolate this equation for un plus 1. And then we end up with equation 18. And now the last step is the new pressure can be obtained using this equation. We isolate for Pn plus 1. So this is why this incremental projection method is also called pressure correction method, because we now also have to estimate the new value of pressure by correcting the pressure. So that means the value of phi that was calculated by solving the Poisson equation, now we need to add the pressure evaluated at the all state. So we have equation 19. So now the algorithm for the incremental method is the following. So the first step to solve the Navier-Stokes equations is that we need to initialize the pressure and velocity fields at time t equal to 0. So we will assign values to Pn and Un, and then we will fix boundary conditions. Now we enter the temporal loop, and you can notice that this algorithm is very similar to the non-incremental version. The only difference is that we need to solve the Poisson equation to find phi. Once that you find phi, you can correct the velocity, and now you have to compute the new pressure using equation 19, and then you update all the fields to be used in the next time loop, and again you exit the temporal loop, but now you increment the time and return to step 2 until the final time is reached. The difference is that one of the advantages of using the incremental version is that this algorithm tends to be of order delta t squared. So that means that it's going to be slightly more stable compared to the non-incremental version, because you can use moderate large or middle values of delta t, and your method is going to be stable. You will avoid some unphysical oscillations of your solution of the velocity and pressure using the incremental version. And now I would also like to explain a bit about the semi-implicit Euler. So the explicit Euler, which is the temporal discretization method that we described here. So as I was saying before, the explicit Euler needs small values of t, of delta t, to be stable. So in CFD, we tend to use the semi-implicit Euler method instead because it's slightly more stable. So that means that in order to evaluate our variable, you compare it with the explicit Euler method, that all the right-hand side of the equation depends of the old state. That's why I wrote this equation. But in semi-implicit Euler method, there are also going to be terms that will depend on the new state. So we cannot use an algebraic equation to evaluate the velocity compared to equation 14. So instead, in semi-implicit Euler method, we will end up with a system of equations that will have the form, the following matrix form, where A is a matrix of coefficients, U star is our vector of unknowns or vector of variables, and the vector R is a vector of source terms or constants. And for the semi-implicit method, the viscous term will be implicit, so as you can see here, while the convective term will be estimated at the all-time n. This is just to linearize the system. So now we have equation 20, which was discretized using the semi-implicit method. You can notice that we have the Laplacian in terms of the intermediate velocity. We have the pressure evaluated at the all-time, the source terms evaluated at the all-time. Also, the convective term is evaluated at n. So now we will consider a pressure Pn to calculate the intermediate velocity U star. So this is the incremental projection method because we are considering Pn to evaluate U star. So this equation becomes, so we have equation 20 that has to be solved to find U star. Remember, we also have to satisfy the incompressibility condition, and the non-incremental version can be obtained when this pressure gradient is equal to 0. So semi-implicit Euler, here I'm giving an example of discretization of the Navier-Stokes equations, equation 20. So let's consider the two-dimensional case. That means when t is equal to 2, and the Laplacian of the intermediate velocity. So that means this term can be discretized using a second-order central difference scheme. So I talk about this method, a spatial discretization method, in my finite difference method video that can be found in my channel, that I will include in the comment section. So here I express the Navier-Stokes equations. These equations have to be solved in a cell. So this cell has a specific location, which is represented with the indices I and j. So we need to evaluate the velocity at the faces of the cell. So these indices I and j represent the locations of our cell faces. So for instance, we have to solve the Navier-Stokes equations for each face of our cells. So in order to evaluate these Laplacian terms, we need to use the second-order central difference scheme, and to evaluate the second derivatives of the velocity U star, we need to use 3 points. the first one is the velocity value at a specific location. Then we need to evaluate the velocity at the cell to the right, and then the velocity at the cell to the left. And yeah, here we evaluate the first second derivative of u star in x direction. But here we have to evaluate the second derivative of the velocity, but now in y direction. So that means that we need the value where we are solving, the value of the velocity where we are solving the Navier-Stokes equations. Then we also need to consider the value of the velocity at the top cell, the cell above, and then the velocity value at the cell at the bottom, the cell below, to estimate the Laplacian in y direction. And also, yeah, we need to estimate the value of the velocity field in the previous time step, and then all these terms are can be also evaluated at the time step, at the previous time step, which is the pressure gradient, the convective term, and the source term. Here I'm not illustrating the discretization of the convective term, because that's another topic that I would like to discuss in the future. But the idea here, I'm showing equation 22 because this is the equation, the Navier-Stokes equations using the semi-implicit Euler method, and this equation can be expressed as a system of equations that can be assembled into a metric system of this form, the form that I described before. So, incremental projection method using the semi-implicit Euler is not really different compared to the methods that I showed before. We also have to correct the velocity, the final velocity, using this equation, equation 23. We will also define the variable phi to obtain a Poisson equation in terms of this variable phi. And then if we apply the divergence operator in both sides of the previous equation, and then considering the incompressibility equation for the new velocity, we will have a Poisson equation for phi that can be solved. We have equation 24, and then once that we solve the Poisson equation for phi, we can correct the new velocity with equation 25, and then we also need to correct the new pressure, or to obtain the new pressure using equation 26. So the algorithm for the semi-implicit incremental method is very similar to the algorithms that I previously showed. The only difference is that we need to solve the momentum equation in matrix form. So that means that we need to solve this matrix system. Is a matrix of coefficients. U star is our vector of unknowns, or vector of variables. And yeah, R is a vector of constants or source terms. And then once that we solve this matrix system, we will obtain the non-divergence free velocity U star. Once that we have this information, we can solve the Poisson equation to find phi. With both U star and phi, we can correct the velocity u n plus 1, and then we can now obtain the new pressure p n plus 1, and then we update all the fields to be used in the next time loop, and then we increment time as follows, and return to step 2 until the final time is reached. So this incremental version is also of order delta 2 square. So final points. As I mentioned before, the non-incremental version tends to be of order delta t. The incremental version, on the other hand, has a splitting error, which is unrelated to the time discretization. So this incremental version of the projection method is of order delta 2 square, which allows us to choose second order accurate methods for time discretization. So instead of semi-implicit Euler method, we can also use more accurate methods for temporal discretization, such as Crank-Nicholson, and so on. You can find more information about this in this paper. And the explicit methods that I showed before for temporal discretization of the Navier-Stokes equations are of order delta t. So you need to be, if you use these methods, you need to be very careful by using the values of delta t in your simulations, because if you use slightly large values of delta t, you might experience some instabilities in your simulations. So here are some references. So these projection methods, I actually use those methods in my previous research work to solve the Navier-Stokes equations or the momentum conservation equations for complex fluids. And if you want to know more information about my work using these projection methods, here I include three of my research papers that were published in the last 2 years. So you are welcome to check them out if you are interested.